Have you ever heard of quantum key distribution, or also known as Protocol BB84? I'll talk you through how it works. First, here we have Alice, who needs to send an encryption key to Bob, but wants to make sure it's not intercepted. Let's try using quantum key distribution. Let's start with Alice, whose first bit is 1. Now Alice has a choice of applying an H gate or a no gate, in other words called the identity gate. She chooses the H gate, causing her qubit to go to the minus phase superposition. Now, Bob also has a choice of whether to apply the H gate or the I gate. He chooses the H gate, causing Alice's qubit to return to the 1 state. Once Bob measures this qubit, he gets the measurement of 1. Now let's walk through a different scenario. Alice's next bit is 0. She again chooses the H gate, resulting in a plus phase superposition. Bob decides to choose not to apply the H gate this time, causing the qubit to stay in the plus phase superposition. When Bob measures the plus phase superposition, he can get the equal chance of 0 or 1. In this scenario, Bob ends up with 1, even though the original qubit that Alice gave him was 0. This process goes on until Alice has sent every single bit to Bob, who may or may have not gotten the correct value. So how will they finally get a secret key? Well, that's the next step. Only Alice knows the bits that she sent to Bob, and Bob only knows the bits that he measured. But to agree on a final key, they both share what gates they used for each bit through a public channel, whether they use the H gate or no H gate. If the gates match, they then use that bit as part of the final key as seen here in the table. Quantum key distribution is incredible, as it allows two people to share encryption keys with security guaranteed by the laws of quantum physics.